What if I told you that the same basic idea behind a hot glue gun helped spark a manufacturing revolution that's now worth over $20 billion a year? That's not an exaggeration. The core technologies behind 3D printing are simpler than most people think, and once you understand them, you'll see why industries from aerospace to medicine can't stop talking about them. In this video, you're going to learn the 5 core additive manufacturing technologies, how each one actually works, what supporting processes make them possible, and which industries rely on them most. By the end, you'll have a solid foundation that most engineers spend years piecing together on their own. Let's get into it. Section 1. Material extrusion. Let's start with the technology you've probably seen most. Material extrusion, often called FDM, which stands for Fused Deposition Modeling, works almost exactly like that hot glue gun analogy. You feed a solid material, usually a plastic filament, into a heated nozzle. The nozzle melts it and deposits it layer by layer onto a build platform. Each layer fuses to the one below it, and over time you get a complete three-dimensional object. The reason this process became so popular is cost. The machines are relatively inexpensive, the materials are widely available, and the technology is easy to operate. That's why you'll find FDM printers in schools, startups, and hobbyist garages all over the world. But there are limitations. The surface finish tends to be rougher than other methods, and the mechanical properties, meaning how strong and consistent the part is, can vary depending on the direction it was printed. Engineers call this anisotropy, and it matters a lot when you're designing parts that need to handle stress in multiple directions. So material extrusion is fast and affordable, but what if you need much finer detail, or you're working with materials like metal? That's where things get really interesting. Section 2. VAT PHOTOPOLYMERIZATION. Imagine a tank of liquid that turns solid the moment light touches it. That's the fundamental idea behind VAT photopolymerization. This category includes 2 well-known technologies, SLA, which stands for stereolithography, and DLP, which stands for digital light processing. In SLA, a laser traces each layer of the design across the surface of a liquid resin. Wherever the laser touches, the resin hardens. In DLP, instead of a single laser point, an entire layer is projected at once using a digital light source, making it faster in many cases. What makes this process remarkable is precision. VAT photopolymerization can produce extremely fine features and smooth surfaces, which is why it's widely used in dental and jewelry applications where detail is critical. A dental crown or a mold for a custom ring needs to be nearly perfect, and this technology delivers that. The trade-off is that the materials, called photopolymers, can be brittle and sensitive to UV light over time. They're not always ideal for functional mechanical parts that need to survive real-world conditions. But what if you need strength and precision together? What process could possibly combine both? Section 3. Powder bed fusion. Powder bed fusion is where additive manufacturing starts to get serious about industrial applications. The basic idea is that a thin layer of powder, either plastic or metal, is spread across a build platform. Then, a laser or electron beam selectively fuses the particles in the pattern of that layer. The platform drops slightly, a new layer of powder is spread on top, and the process repeats. 2 of the most common versions are SLS, selective laser sintering, which typically uses polymer powders, and SLM, selective laser melting, which fully melts metal powders to create dense, high-strength metal parts. This is the process that aerospace companies use to print turbine components, that medical device manufacturers use to print titanium implants, and that automotive companies use to prototype complex brackets and housings. The parts produced can have mechanical properties comparable to traditionally manufactured components, which is a huge deal. One major advantage is that the unfused powder around the part acts as its own support structure, which means you can print complex geometries without adding extra support material. One significant limitation is that the equipment and materials are expensive, and managing fine metal powders requires strict safety protocols. So powder bed fusion handles complex, high-performance parts beautifully. But what if your part needs to combine multiple materials or colors in a single print? Section 4. Material jetting and binder jetting. These 2 technologies sound similar, but work quite differently, so let's take them one at a time. Material jetting works a lot like a standard inkjet printer, except instead of ink, it jets tiny droplets of photopolymer material onto a build surface. UV light immediately cures each droplet as it lands. Because different materials can be loaded into different print heads, you can produce parts with multiple materials and even full color in a single build. This makes it incredibly useful for creating realistic prototypes, medical models, or product mock-ups that look and feel close to the final version. Binder jetting, on the other hand, spreads a powder layer similar to powder bed fusion, but instead of using a laser, it deposits a liquid binding agent that glues the powder particles together. The resulting part is actually quite fragile at this stage. It needs to go through a post-processing step, typically sintering or infiltration, to become strong and usable. Binder jetting can work with metals, ceramics, and sand, making it versatile for industrial tooling and casting applications. Both of these processes highlight something important. The printing step is rarely the end of the story. Post-processing is often what determines whether a part actually works. Which brings us to the topic that most beginners completely overlook. Section 5. Supporting processes. Here's something that surprises a lot of people. The 3D printer itself is only part of the equation. Supporting processes are what transform a raw printed part into something functional, precise, and reliable. Support removal is one of the first steps. Many technologies require support structures to hold overhanging features during printing, and removing those supports, whether by hand, chemical dissolution, or water jetting, takes skill and time. Heat treatment is critical for metal parts. Processes like stress relieving and hot isostatic pressing, sometimes called HIP, remove internal stresses and close-up microscopic voids, improving the mechanical properties significantly. Surface finishing includes sandblasting, tumbling, polishing, or machining to achieve the required surface texture. Some applications demand a mirror-smooth finish, while others just need to meet a dimensional tolerance. Inspection and quality control close the loop. Technologies like CT scanning and coordinate measuring machines verify that the part matches the original design within acceptable limits. In industries like aerospace and medical devices, this step is non-negotiable. Understanding these supporting processes is what separates someone who can operate a 3D printer from someone who can actually engineer with one. And that's your complete overview of the core additive manufacturing technologies and the processes that support them. You now understand material extrusion, vat photopolymerization, powder bed fusion, material and binder jetting, and why post-processing matters just as much as the printing itself. If this video gave you a clearer picture of how these technologies actually work, do me a favor and hit the like button right now. It genuinely helps more people find this content. Subscribe so you don't miss the next video, where we go deep on design principles specifically for additive manufacturing. And drop a comment below with one question you still have about 3D printing. I read every single one and I'll answer yours directly. See you in the next one.